Hello everyone and welcome to Growing 5.3. Today's learning targets, we're going to be able to correctly understand how the rules for integral exponents is related to rational exponents. What is rational? Well, we should remember that rational starts with ratio, and ratio is another word for fractions. So if our exponents are in fraction or rational form, are the same rules going to work that we found for our integral exponents? Our ACEs work for 5.3 is going to begin on page 90. It's going to be numbers 26 through 36, 72 through 74, and 79 through 81. So if we turn to page 80 in our books, we're going to find 5.3 extending the rules of exponents, and it tells us that we investigated some rules in 5.1 and 5.2, and we found all of the following to be true as long as x and y were not 0 and that m and n are integers. So the question in 5.3 is, will these rules still work for rational exponents? And again, rational is the same as being a fraction. So the question, suppose a certain amoeba population quadruples every week. If we start with one amoeba, then the population y grows according to the relationship of y equals 4 to the x. That's the equation we've come up with. So it shows us the graph of the relationship down here. Now the question is, does it make sense to write y equals 4 to the 1/2 power if we want to know when the population of amoebas was 2? Because after 1 week we know it's 4. At 0 weeks there was 1. So we know at some point in time between 0 and 1, and when it got from 1 to 4, that it had to probably double at some point in time. So we want to find out when that is. Can we come up with a rational exponent to make that true? So we've done that. We plugged in y equals 4 to the 1/2, and we say that it winds up being the value of 2 here. So the point 1/2 and 2 is a point on the graph that corresponds to that. This means that 4 to the 1/2 equals 2. Well, Chaska then reasons the following. Since you already know that the square root of 4 equals 2, it must also be true that the square root of 4 equals 4 to the 1/2 power. Notice square root, 1/2, those are considered being the same thing. So in the denominator, we have a 2, which is essentially the same as what's in our root down here. It's the second root or the square root that we are looking for. So the next question is, do the rules for adding exponents apply to the exponent 1/2? For instance, is it true that 4 to the 1/2 times 4 to the 1/2 equals 4 to the 1/2 plus 1/2, or 4 to the first? Well, if we consider that 4 to the 1/2, okay, is equal to 2, then if we take 4 to the 1/2 times 4 to the 1/2, that would be 2 times 2, okay, which is going to equal 4. So we should be able to add 4 to the 1/2 to multiply 4 to the 1/2 times 4 to the 1/2 and get the 4 1/2 plus, that's a half by the way, plus 1/2, or 4 to the first. So what we know then is that the same rules that we applied to integral exponents or integer exponents is the same for rational exponents. Chaska then thinks about other roots, as in the cube root of 8 equals 2. So could we write 8 to the 1/3 power? Okay. Again, notice what I have for my denominator is what I'm putting in the root. Okay, 8 to the 1/3 would then equal 2. Okay. So if we skip down to, in general, the nth root of a number b, okay, this is just any number b, the nth root of that is denoted by the nth root of b, or b to the 1 over n. So we want to think about what Chaska found about what the 1/2 and 1/3. Is this then true? The nth root of x equals x to the 1 over n? Yes, it is true. Then we need to figure out, do the other rules for exponents apply to exponents that are fractions? In problem 5.3, we're going to explore whether the rules for those integral exponents apply for rational exponents. Let's take a quick look at part A. It says, what does 16 to the 3 halves mean? Well, Marie, Latrell, and Jacayla came up with 3 different ways to think about 16 to the 3 halves. Do any of them make sense? And then explain, 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 okay, why it doesn't make sense. So Marie's method is 16 to the 3 halves is 16 to the 1 half cubed, which if we take 16 to the 1 half, we're looking for the square root of 16, which is 4. You take 4 to the 3rd power, 4 times 4 is 16, times 4 again is 64. That seems to work. What about Latrell's method? Latrell wants to take this 16 and 3 halves and cube 16 first, which would be 4,096, and then to take the square root, or 1 half power, of 4,096, which is the square root of it. That also comes up to be 64. Finally, Jacayla's method is taking a 16 and 3 halves equals 16 to the 1st plus 16 to the 1 half. Okay, which if we break those up means 16 to the 1st times the same base, 16 to the 1 half. Well, 16 to the 1st is going to remain 16, and 16 to the 1 half means we're trying to find the square root of 16, which is 4. So now we have 16 times 4, or 64. So all 3 of these appear to work. We get the same answer. So taking these methods, one of these methods, find the value of each of the following and show your method. Okay, show me how you can do that. In B, we want to take what we learned about our integral roots and our integral numbers, roots. Let me try that again. Take the rules we found about our integrals with our exponents and see if we can come up with those same rules being applied to rational exponents. So if 4 in the 3rd times 4 to the half, does that mean since we have the same base that we can go 4 and 3 halves plus 1 half? As in 4 and 3 halves, okay, plus 1 half, or we're going to have 4 the 4 halves, which is actually 2. So we have 4 squared. Can we do that? Does that all prove out to be true? And then carry on the other rules for exponents that we learned in 5.1 and 5.2 and see if you can apply them for the rest of B. And we're going to skip part C, and then we jump to part D. It asks you to look back at problem 1.4, where we were looking at the area of a ballot. And from that, we have our 3 people came up with 3 different equations. I want you to be able to tell me if these are all correct or not. And again, explain, explain, explain. Finally, in E, again, we want to say the rules of exponents. Can we write equivalent expression for each of the following? So what's another way to write this so that we have one base and one exponent for each of these is what I would like you to get them to. So that's what we're looking at in 5.3, checking out if our rules for integral exponents work for rational exponents. Reminder, 5.3 ACES questions 26 through 36, 72 through 74, and 79 through 81. Looking forward to seeing your challenges and questions in class.